All right, hi Science 7 students. This recording is going to help you prepare for the next test, which is going to be on March 29th. Just one test to go before your spring break, so keep up the hard work before spring break, and then hope you guys have an awesome spring break. You guys have worked hard, so you can enjoy it then. So I hope you guys are enjoying the warmer weather. I know it's not quite spring yet, but starting to hint of spring, and hopefully in the next little while it's going to look a little more like spring. So anyways, speaking of ice, as we could be talking about this time of year, the formation of ice from water can be beautiful and also mysterious, as you can see in this picture here. Absolutely gorgeous looking iceberg here. So you'll recall that there are different states of matter that solids and liquids and gases are found in. So those are known as the three states of matter: gases, liquids, and solids. And remember, in order to go from one type of matter to another, you add heat energy. For instance, if you're going from ice to water, you add heat energy. And if you're going the other direction from liquid water to ice water, you're going to have to remove heat energy. You know, sometimes people talk about it's really cold. You know, we opened up the window and the cold came in. But actually that never happens. You don't actually have cold coming into a room. It's always heat either entering or going out of the room. I remember one time I was watching, I don't know if you guys have ever watched The Magic School Bus. I was watching that with my kids. And you've got the teacher named Ms. Frizzle on the show. And Ms. Frizzle was talking about that. One of the kids was sitting near a window, and they had some cocoa or something like that. And it started getting cold because the window was open. And the kid said, well, hey, it looks like the cold's coming in. And Ms. Frizzle said, well, actually, it's the heat that's coming, leaving your body and going to the outside that's happening. So anyways, let's just go over the first question here. And you guys will notice that these are the same questions that are from lesson number 25, which is a review lesson. But I really think that going over these in the whiteboard recording here is going to help you to remember them a lot better on the test. So let's look at the first question then. It says the reason why liquid water changes into ice is that blank is removed from the water. And so that's going to be heat removed from the water, right? Because as we said, it's always heat either entering or heat leaving a situation that's changing from one state of matter to another. Okay, so as you can see, heat is going to be removed from water. So we have a picture here that's showing the different states of matter going from one to another. This is a really good diagram to know. And just to see these different points, you know, from going from one point to another, you have solids going to liquid, solid ice going to liquid water, that's melting. The other direction is freezing, that sort of thing. So again, the melting point is when you go from solid to a liquid, and the opposite of melting is freezing, and that's of course going from liquid to solid. So again, we have two words that are opposites here. It's good to know which words are paired with each other. And then you also have evaporation. So you got evaporation of water. You've got a puddle, for instance, and it's evaporating in the heat. It goes from liquid to a gas. If you go from the opposite, a gas to a liquid, that's condensation. And it's good to know the word condense means to get thicker. So when you're going from a gas, like steam, to liquid, of course the molecules are becoming thicker, right? So again, remember, evaporation and condensation are also paired together. Then we've got this one that's kind of a little bit different. It's going all the way from a solid to a gas, and you're skipping the liquid phase, or from a gas to a solid. Either one is sublimation. We don't talk about that one so much because it doesn't happen that often. All right, so let's look at just a little bit of info on this page. Okay, the freezing point is 0. But that's also the melting point of water. Okay, so right at that point you have things either freezing or melting. And so again, we talked about how freezing and melting are opposites, and evaporation and condensation are also opposites. So question 2 says the point at which a solid changes into a liquid is known as, okay, so for instance, solid ice going to liquid water, of course that's melting, right? And I wrote here the freezing point and the melting point of water are both 0 degrees Celsius. Okay, awesome. So we got the two answers right here. We'll go on to this stuff here. It says think about what happens in nature. So, okay, it talks here about how evaporation happens in lakes. So, of course, you've got the evaporation of water. Water is going up, and eventually it cools as it goes up high, and then it condenses. And that's when it falls as water. Okay? So that's condensation. If you think about condensation in your home, if, for instance, you've got some boiling water, you take a cold jar full of ice, you put it near the boiling water, you're going to have liquid water forming on the outside of the jar. And why is that? It's because it was cooled. The steam rising was cooled when it hit the jar, and it formed liquid water. Okay, so again, looking at the next answers, when water from lakes is changed into steam, this process is known as evaporation, right? Question 5, when liquid forms on a cold window that's placed near a pot of boiling water, that's the process of condensation. So again, condensation is going from the gas or steam that you have, and then it forms liquid water on the outside of the jar. We've got a picture of this here. This could be condensation forming on the outside of a, for instance, outside of a bathtub. If you have a shower door, that sort of thing. Okay, so question 4 says when water from lakes is changed into steam. Okay, so this is the answer we looked at already, evaporation, and question 5 was condensation. All right, so you remember what heat energy does to the tiny particles that are in a solid, liquid, or gas? Well, it causes the particles to hit each other and then to spread out, okay, because they've got more energy, so they spread out. It's just like if people have a bunch of energy, they're moving around, they're going to hit each other and spread out. So the particles in ice or solid are close, but as heat is added, the particles spread out. Then as heat continues to be added, liquid is changed to gas or steam, and at this point the particles are really spread out. So the particles are closest together in a solid, and they're furthest apart in a gas. And remember, the warmer a substance, the more energy it has. So the more energy it has, the faster the particles are moving. And so in other words, solid particles have the slowest moving particles, liquid particles have faster particles, and gas particles are just zipping around. You know, if you're talking about hydrogen molecules that are in the air right now, they're actually zipping around at about a mile a second. Now other particles like oxygen are not quite as fast, maybe about a quarter as fast as that, but that's still really fast. So even though you can't see them, they're just zipping around. All right, so let's just compare solids, liquids, and gases in some different areas. So as far as how close the particles are, again, they're closest in solids, furthest apart in gases. So because the particles are close together, the volume of a solid is smaller than the volume of a gas, because volume is how much particles you have in a certain amount of space. So the volume of a solid is going to be occupying less space. Okay, so because the particles are spreading out, they're going to take a larger volume of space. All right, solids have the least amount of energy, but when energy is added, of course, we heat something up, it turns into a gas, so gases have more energy. Okay, so solids are colder, gases are warmer, and the particles in solids move more slowly because they have less energy. Gases have more energy and they move fast. Okay, so when particles are heated, they do a number of things. First of all, the molecules that are beside each other, they start to vibrate, and then they move with more energy. Eventually they spread out, and as we saw, their volume increases. Okay, so as you can see, this is solids. The particles are close together. They don't move around very much. They're just kind of vibrating back and forth a bit. Whereas liquids, the particles are further apart. They can slip past one another. Particles are moving more. With gases, the particles are really far apart and they're zipping around. Okay, so let's look at the next batch of questions. Question number 6, the state of matter which has the smallest spaces between the particles. Okay, well that was the volume. Sorry, that was the solid, right? That's what I meant to say. Okay, question 7, when you compare solids, liquids, and gases, which particles will be moving most quickly? Well, we saw that gases are moving most quickly. Of course, they have the most energy, right? And they're just zipping around, right? When solid particles are heated, a number of things happen. First, the particles start to vibrate, then they bump and spread out. And when particles spread out, this means the volume of the substance becomes larger. Okay, so volume is the amount of space something takes up, right? Okay, so again, please practice these after you watch the recording. Make sure you can get these answers. Another thing I wanted to mention, guys, I just thought about it. When you write the test, when you're looking at the matching questions, they're ones that have fill in the blanks, always make sure that you use the actual options for the blanks. So for instance, I might have 8 fill in the blank questions, so I write down 8 words. So you need to choose from those 8 words. If you choose other words, you might be close enough to get the mark, but you might not. So it's really important to choose from those 8 words or whatever it is. Okay, so when we compare solids, liquids, and gases, solids are different than both liquids and gases in one way. Solids keep their shape, whereas volume, or both their shape and their volume, no matter what you put them in, whereas liquids and gases don't. So if you have a solid brick and you put it in a box, it still keeps its shape, right? Whereas if you take something like a liquid, like maple syrup, for instance, it takes the shape of whatever container you put it in. Same with a gas. You put it into a balloon, it takes the shape of the balloon, right? Okay, now we're going to look at 2 different types of energy that are actually kind of related. Thermal energy and kinetic energy. Now remember that thermal energy is just another way of saying heat energy. What is kinetic energy again? Well, that's the energy that any moving object has. So if a person's running or a bullet's moving, that they all have kinetic energy. So the faster an object moves, the more kinetic energy it has. Okay, so let's look at these questions. Unlike liquids, solids always have a definite shape and volume, okay, whereas liquids don't. And neither do gases. Okay, question 10. The type of energy which any object that is moving possesses is known as kinetic energy. So again, kinetic energy is the energy of motion. All right. So, remember we talked before about how much thermal energy a certain object has? And the amount of thermal energy or heat energy an object has is equal to the total amount of kinetic energy it has. In other words, kinetic energy is the energy of motion. So the more its particles are moving, the more heat there's going to be, right? So it makes sense that there's a connection between thermal energy and kinetic energy. So if you have a pot and a cup, so the pot's bigger, right? They can be at the same temperature, but even though they're at the same temperature, they don't have the same amount of thermal energy because there's far more particles in the pot than the cup. Now remember, when we talk about temperature, temperature is the average amount of kinetic energy of a substance. Okay, so you have the particles moving around at different speeds. That's the kinetic energy that they will have, depending on how fast they move. But the average amount of kinetic energy they have is going to be their temperature. So again, both a small and a large object can have the same temperature, but they'll have different amounts of thermal energy. Okay, so now consider the following, as Bill Nye would say. I don't know if you guys ever watch him. He's pretty cool. So again, this is just going over what we were talking about before. If you had a pot and a cup of soup, they could have the same temperature. But because the large pot has more particles in it, it's going to have more thermal energy or more kinetic energy. than the cup will have. Okay, so a few more review questions. A cup of hot chocolate and a pot of it would have the same temperature, but since the pot has more particles, it will have more, you could say it will have more kinetic energy or more thermal energy. So the thermal energy of a substance is the total amount of kinetic energy of its particles. Remember, thermal and kinetic energy are related together. All right, the average kinetic energy of a substance is known as the temperature. So remember, temperature is always an average amount of the kinetic energy. All right, so remember we talked about different types of heat energy or thermal energy. We talked about the sun, for instance, or fire, or actually if bacteria are breaking something down. So if you've got, say, something decomposing in the backyard, maybe your mom put some scraps of food back there and they decompose, there's actually heat produced, and sometimes it's quite a bit of heat that can be produced by the bacterial decomposition. Okay, so remember when we were talking about solar energy, this is a picture of the sun. So the sun's energy is solar energy. Now, where does solar energy come from? That energy actually comes from nuclear reactions that are taking place on the surface of the sun. Now, you guys might be familiar with the term nuclear energy, and you might be familiar with what's going on in Japan right now with all the stuff that's been happening there, and the fact that they have some nuclear reactors over there that have been unsafe because some of the waste is getting out and that sort of thing, so they have to bury it, and they're trying to come up with a solution, you know, how are you going to contain all that nuclear radiation, and they're thinking about possibly putting it in concrete or something like that. So now we're going to talk about different kinds of solar energy. So solar energy is pretty cool, you know, using the energy from the sun, because you're using free energy, right? It's not like fossil fuels and that sort of thing. Now there's two different kinds of solar heating that people can use. In places like California where they get a lot of sun, they'll put these black tubes and you'll have them wind back and forth and back and forth, and they're carrying water or maybe antifreeze or something like that, and they're heating up from the sun, and then they take that energy into the house and heat up the house. Now that is called active solar energy. So when you have pumps and pipes and that sort of thing, that's active solar energy. This picture here is a picture of a passive solar system. And so really you don't have any special equipment for a passive solar system. All you've got is, say, a window that lets the sun in. And if it's south facing, then that's a bonus because it's letting in the sun in the right place. Okay, so that's the difference between passive and active solar energy systems. Okay, so let's try a few questions here. The sun, forest fires, bacteria decomposing dead creatures, and electric heaters are all source of course, heat energy or thermal energy. Question 15, the nuclear reactions on the surface of the sun are the cause of solar energy. That's the sun's energy. And the type of solar heating system which involves a house being heated directly by the sun is known as a passive solar system. Okay, so that's just direct heating. You're not putting in those extra things in between that are involved in the heating, like the tubes. It's just direct heating from the sun coming into the window. Okay, so of course humans are able to get thermal energy from man-made devices like heaters, but it doesn't matter what kind of energy you're talking about. Energy is always measured in joules. So you might want to think of a phrase like Julie has lots of energy to help you remember that joule is a type of energy. So heat, which is a form of energy, is measured in joules. Now if we're talking about power, that's kind of a different ball of wax. Power is measured in watts. And if you think about speakers, we often talk about really powerful speakers having a lot of watts. The bass speakers are the woofers, right? And the tweeters are the ones that make the high sound. All right, so question 17, the units that are used to measure heat or any type of energy are joules. So remember, since Julie is really energetic. Question 18, power is measured in watts. So think of what powerful stereo speakers are measured in. And watts are named after a guy named James Watt. Okay, so we're going to talk now at this point about heat transfer. So remember, heat is not a substance, it's a form of energy. And heat always moves from one area to another area. It moves from wherever it's hot to wherever it's cold. So if one room in the house has a heater and it's hotter, that heat is going to spread out eventually into the other parts of the house where it's colder. Now there's another way of saying that. We can say that heat moves from areas that have high kinetic energy to areas that have low kinetic energy. Now you remember these different words we use to describe different types of heat transfer? One of them is conduction, and that happens mainly in solids. So when particles are close to one another in solids, they bump into each other and they transfer their heat energy when they're vibrating back and forth. It's kind of a chain reaction. Okay, so you can see solids here, conduction's going on, and the particles are moving or passing on their energy one to another as they vibrate back and forth. So question 19, the definition of blank is the flow of energy, so that's going to be heat, is the flow of energy from where there is more kinetic energy to areas where there's less of it. Question 20, materials using solids which allow heat to be transferred through them easily are known as conductors. So this could be a conductor, if this was metal, for instance. Alright, so when conduction occurs in solids, the particles start to vibrate and transfer their heat energy from one to another in a chain reaction. Alright, so we've looked at conduction in solids. Now in liquids and gases we can have convection. Remember, when hot air rises from the vent to the floor, and then cool air moves in to take its place, we get a convection current going on. And that happens in air in your house through the heating system, and it also happens in, for instance, in a pool. So it happens in liquids and gases. Okay, so radiation is a different type of heating. It's usually produced by a solid, and so any solid object can radiate energy into space. Now radiation energy doesn't require any substances in order to work. It doesn't require solids, liquids, or gases. It actually requires empty space. So the energy that comes from the sun is actually traveling through a vacuum, which is empty space, all the way from the sun to us. And that's why it can travel so quickly. Alright, so remember then that radiation is produced by a solid object. If you think of, for instance, a heating element, if you put your hand above it, that's radiation that's causing it to move so quickly towards your hand. Okay, so question 22, convection currents occur only in liquids and gases. A circular pattern forms as hot substances rise and cool substances move to take their place. Question 23, heat that travels through a vacuum, example solar energy traveling through space, is known as radiation. Okay, so we've already seen that a conductor is a substance that is good at transferring heat through it, so a metal is a good conductor. Remember, conductors and insulators are opposites. So an insulator is poor at transferring heat through it. So plastic would be a good example of a conductor, or an insulator, sorry. Okay, so if you had a pot, the metal part would be a conductor, and the plastic handle would be an insulator. So when you think about insulation in a home, insulation actually does two things. It always prevents heat from moving, because of course it doesn't involve cold. So it stops heat from moving out of our homes in the winter, and it stops heat from moving into our homes in the summer. A lot of people don't realize it does both those things. Now, there are also some special kind of windows that can help you to keep the heat in your house in the winter, for instance. They're known as argon gas windows. And here's how they work. Well, one problem with windows when you have a double paned windows is that you've got air moving between the two windows in a convection current. Well, that convection current that happens allows the heat to be lost from the pane on the inside of the house to the pane on the outside, and that's why we lose heat energy in the winter. And that's bad, of course, so that's why we want these argon gas windows that help us to lose less heat. Okay, so just a refresher again, something like a curling iron is part conductor, that's going to be the metal part insulator, that's going to be the plastic part. And when we talk about these argon gas windows, because argon does not move around in a circle very much like air does, it does not allow heat to be transferred as much from the inside of the house to the outside of the house. Okay, so again, some more review questions. A metal pot with a plastic handle is an example of a conductor, that's the metal part, being used together with an insulator, that's the plastic part. Question 25, blank is used to keep a house warmer on a cold day and cooler on a hot day, that's going to be insulation. Question 26, the reason why argon gas is used as in an energy efficient window is that unlike air, argon does not move much, so air currents are not bringing heat to the outer window pane like they do with regular windows. Okay, so we know that when solid objects are heated, they expand, and when you cool them, they contract. So a piece of metal is going to get longer when it's heated and shorter when it's cooled. Shorter is another word for contracting. Contracting is another word for shorter. So also we know that dark objects absorb heat, while white objects, or shiny metal objects, reflect heat away. And that's why we want to wear dark clothing in the winter to absorb the light and heat, and we want to wear light objects in the summer to reflect the heat. Okay, so this here is just showing you a road expansion joint, and thank God for these in the wintertime, because they allow the road to both expand in the summer and contract when it's cooled in the wintertime. And that's good, because otherwise you'd have a lot more breakage of the road because of all the changes in temperature. Okay, so question 27, a piece of metal will expand when heated and contract when cooled. Of course, contract and cool both start with a C, that kind of helps you remember. Question 28, blank colored materials absorb heat, that's going to be dark colored materials, and while light colored materials reflect heat. Okay. So, I got a picture here of a bunch of penguins. I don't know if you guys have ever seen the movie The March of the Penguins. Really cool movie. If you haven't seen it, I really recommend it. These are amazing creatures. As you can see here, they huddle together. They can have, I forget if it's -85 without the wind chill or with the wind chill, but whatever, it's just crazy cold in Antarctica. But when they huddle together, they're protecting their eggs, and their body heat is kept. And so amazing creatures, but people of course can't endure such cold temperatures as that, so people like temperatures that are somewhere between 0 and 45 in order to live in. If it gets much colder than 0, they die, or hotter than 45. So you remember what a thermostat is in your house? Well, that's a device in your house which lets you control what the temperature in the house is. So the important part of a thermostat is something called a bimetallic strip. I'll show you that later. It's a strip made of two metals that expand and contract different amounts depending on what the temperature is. Okay, so here's the coil. So because it's got two pieces of metal put together, and one of them is going to bend more quickly than the other, and that bending causes the dial to go up and down. So that's how a thermostat works. Okay, so when it's cold, that's going to cause the needle to change, which then causes your furnace to kick in. All right, so question 29 says human life can really only exist for very long between temperatures of 0 and 45 degrees Celsius. Question 30, the job of a thermostat is to control the temperature of a house. Uses a bimetallic strip to sense the temperature of the house and adjust if needed. All right, we're getting close, guys. So we're talking about saving energy and resources here. Okay, there's a big move these days to save the environment. And if we use resources over again, that's a good thing, right? Using renewable resources, so like sun, wind, and water, we're able to use them over and over again. Other types of resources are known as non-renewable because they're going to run out eventually. So for instance, fossil fuels like coal or oil are going to run out because, you know, oil is sometimes made from dinosaur fossils. And so of course they're not around dying now, and so it's going to run out. And so copper and gold are some other examples of non-renewable resources. So when we talk about energy, there's three different main users of energy. We use it in our homes to heat, for instance, use it in industries, use it in transportations, buses, whatever. But of these three types, industry uses the largest amount of energy. Now, there's some different ways we can save energy, and they have a lot of lights being produced in places like Safeway or whatever. Energy efficient lighting is a type of lighting which helps people to use less energy. So for instance, fluorescent lights as compared to your regular incandescent old-fashioned light bulbs is a good example of energy efficient lighting. Okay, so now when we talk about heating your homes, there's two different types of heating systems. Most people have a central heating system. So for instance, your furnace is going to send heat to all parts of your home. A local heating system is just going to help you with one room. So for instance, if you put a heater in your room, that's a local heating system. Okay, so this is showing an example of a central heating system. You've got a furnace, produces it for the whole house. So let's look at a few questions here. Unlike a resource such as water, which is a renewable resource, fossil fuels and minerals are examples of non-renewable resources. The three main users of energy in North America are homes, industry, and transportation, and industry is the one that uses the largest amount of energy. One way to cut down on your power consumption at homes is to use energy-efficient lighting, such as fluorescent lights. And unlike a local heating system, a central heating system provides heat for an entire house. Okay, just one last concept to go and we're done. So, when we talk about temperature, I know you guys are probably a lot more familiar with Celsius than Fahrenheit. I grew up with Fahrenheit, but I'm actually kind of used to both types of measuring heat, or measuring temperature, I should say. So what you use, though, is this formula here to find out what the degrees Celsius is if you know the degrees Fahrenheit. So all you need to do, if somebody tells you what the degrees Fahrenheit is, you plug that into this formula, and out pops the degrees Celsius. So basically, Celsius is 5/9 times Fahrenheit minus 32. So for instance, if someone told you Fahrenheit is 40, where we see F in this formula, we just plug in 40. So first of all, we simplify what's in the brackets. 40 minus 32 is 8. And we're going to multiply that 8 times 5/9. How much is 5/9? That's 0.56. So we multiply 0.56 times 8. We got 4.48. So 40 Fahrenheit is 4.48 Celsius. So again, that's just a bit above freezing. All right, so we'll just try one more. So it says, using this formula, 90 degrees Fahrenheit would be how much Celsius? Well, we just plug in the 90 where you see the F. So we have 90 minus 32 is 58. We multiply that by 0.56, which stands for 5/9, and we get 32.48. Now they used to say that to get from Celsius to Fahrenheit, you double the Celsius and you add 32. Well, that only works if it's like 0, because you add double 0 and you add 32, and 0 Celsius does add 32, does give you 32, but the formula, that kind of rule of thumb formula breaks down when you get larger and larger. So in other words, when you got 10 Celsius, you're not going to add 32, you're only going to add like maybe 25 or something like that. So gives you a little bit of an idea though. Anyways, thanks for listening, guys. Keep practicing these over and over again until you can get them all. And I want to wish you guys the best on March 29th, day after my birthday. Anyways, and hope you guys have an awesome spring break coming up. And I'd be interested to find out what you do. But until then, please keep working hard and doing your best. Take care and talk to you later. Bye for now.